So now, still dealing with our vector valued functions, we have r of t, which we defined in the previous video, is some function f of t times I plus g of t times j plus h of t times k. So what is a vector valued function? A vector valued function is a curve traced by connecting the tips of all these different radius vectors. So, if we think about this in our xy plane, because it's easier for us to visualize and draw in two space. So maybe we have some point where we're starting, and this curve is traveling out in some direction over here to the right. So what we really want to recognize is we have some initial radius vector, r of 0, and then maybe we have a vector over here, r of 1, and that would define our second point. And then maybe we have a third vector, r of 2. And I should draw my vector notation on all of these. But those create 3 points, and those 3 points create this curve for our vector valued function. We are connecting the tips of all those little vectors to create this larger vector r of t. So these are all the points, say where t equals 1, where t equals 2, t equals 0, t equals 1, and t equals 2. Right? So we have these vector valued functions. They behave like real functions, especially if we draw them in two space. But now we're going to talk about the limits and continuity for these vector valued functions. And the definition for limits within vector valued functions is actually really similar to the way we define limits for real valued functions, real number valued functions. So there we have our vector valued function. Let it be a vector function with a domain D, L representing the limit. The limit is also a vector. So if I wanted to, I could put my little vector notation. Notice that it is bold. And we say that the vector R has a limit vector L as t approaches t sub 0. And then we write it this way. So this is a traditional limit definition. We just have a vector input for the function that we're finding the limit of, and then the output, the limit, is actually a vector. And we still use our epsilon delta. So for every epsilon that is positive, there exists a corresponding delta, also positive, such that for all of the t points inside the domain, the radius function or my vector valued function minus the vector limit is smaller than epsilon whenever the difference between my t values is between 0 and some also appropriately small delta. And, to calculate the limit of any vector valued function, basically we just need to find the limit of each component scalar function. So for example, I'm going to kind of work this out. If we have some limit vector, L sub 1 I plus L sub 2 j plus L sub 3 k, then we can show that the limit as t approaches t naught of r equals L. And that would be by just simply showing that the limit of each of these functions has that limit L sub 1, L sub 2, L sub 3, right? So what this means is we have the limit as t approaches t sub 0 of f of t, which would be our x component, equals L sub 1. The limit as t approaches t sub 0 of g of t equals L sub 2, and the limit as t approaches t sub 0 of h of t equals L sub 3. So by calculating the limit of each of those scalar components, then we can rewrite this. We can think about what we were looking at, that limit of t as t approaches 0 being some r of t function. That is going to be equal to the limit as t approaches t sub 0 of f of t, I, plus the limit as t approaches t sub 0 of g of t, j, plus the limit as t approaches t sub 0 of h of t, and then we've got k over here. So since we know each of these three limits, this is equal to L sub 1 I plus L sub 2 j plus L sub 3 k. And so, essentially all I'm saying here is when you want to find the limit of a vector valued function, just take the limit as each of those components approaches the same t value. So for example, if we have this vector valued function with each of these three parametric components, if I said, well, what is the limit as t approaches pi over 4 of r of t? Well, that would just be the limit of each of these pieces. And essentially, in this case, it would just be evaluating each of those. So if I plug pi over 4 into cosine t, that gives me root 2 over 2 I. Pi over 4 into sine t, root 2 over 2 j. And pi over 4 into t, that just gives me pi over 4 k. It should be a 4 pi over 4 k. So continuity also follows a similar argument. Let's talk about our definition for continuity of vector valued functions. So continuity for vector valued functions is defined the same way we would define continuity for scalar functions on an interval. So if it is continuous at a point inside its domain, if the limit equals that function value, then the function's continuous at every point within the domain. And if we go back and we think about some vector value functions we looked at in the first video, here we see three vector valued functions, and essentially, since all of their components would be continuous, cosine is continuous, sine is continuous, this linear t is continuous, since all of the components are continuous and the limits would match the function values, then the functions are continuous. Right? So all of these space curves are continuous because their component functions are continuous everywhere inside that domain of t existing within all real numbers. If we wanted to look at an example of a function that is not going to be a continuous vector valued function, this g of t vector valued function I've brought in here, of course, we know that cosine and sine are continuous, but our z component, that is the greatest integer function, which when graphed, it kind of looks like a step value function. So the greatest integer function has a discontinuity at every integer. And since this piece is discontinuous, the vector valued function is discontinuous. All right, in the next video, we're going to talk about derivatives and motion, which is really where we start to get into some more interesting problems with our vector valued functions.